Hello, everyone, and welcome to our first session of the day where we answer the question, why math optimization? And also, we're going to take a look at a couple other questions. What is mathematical optimization and how can I identify potential applications? So, on to the big pressing question. So, to take a look at why mathematical optimization is a extremely useful tool, let's first look at what industries and business problems mathematical optimization is used. So, who uses it and what problems does it solve? Next, we're going to look at predictive analytics versus prescriptive analytics. So, what questions does mathematical optimization answer specifically, and how does this differ from machine learning? Then we'll see, okay, after we compared them a little bit and said this is what they do differently and kind of what they do similarly, we're then going to look at machine learning and mathematical optimization and say that, hey, yeah, they can coexist. So, how can these approaches work together? Then we're going to go through a quick tour of mathematical optimization. So, how can I translate a decision problem to an optimization model, and what are the key building blocks to do so? Let's take a look at industries that commonly use mathematical optimization and look at a few of the examples of the business problems that are solved there. So, supply chain analytics essentially it's a bread and butter application of optimization modeling. Where am I opening my next location for my facilities? How am I routing trucks? Where am I putting inventory to make sure that demand is met timely? Those are common supply chain questions, and those questions and problems are solved with mathematical optimization very frequently. Related to supply chain is manufacturing, so production planning, scheduling, workforce planning. Again, sort of bread and butter, very common mathematical optimization applications and the problems that they solve there. Airlines for crew scheduling and flight to aircraft assignment. Energy is another is an area in which there's been some a little bit more emerging application. Your typical sort of I guess classical supply and demand, making sure that you have enough energy to meet demand is it has been happening for a while, and it's a classic application of optimization. But things like resource planning to meet CO2 emission targets, that's a newer problem, and that's a difficult problem to solve. And mathematical optimization is at the forefront of making sure that those targets are being met. Finance is another area in which mathematical optimization is growing and expanding a little bit. You might think of portfolio optimization as something that could be pretty simple and straightforward. Like, hey, I want to buy stocks or I want to sell them. If I think a price is going to go up, I should probably buy. If it's going to go down, I should probably sell. Very simple decision there. But when you think about for all the stocks that exist, for all the customers you may have, it becomes a very complicated problem to make sure that your portfolios are optimized. And lastly, sales and marketing. So doing things like campaign optimization and even allocating sales territory is something that can be done and typically is done with mathematical optimization. So uh, we just talked about some of the industries and business problems. Maybe you're thinking, all right, give me some names here. I really want to know who uses this technology and what are they getting out of it. Well, here's a set of customers that we at Garobi have. So we have uh, companies like Google and Microsoft, the NFL, which I'll highlight in a second, their application, Starbucks, HP, and these are companies that are sort of all over the place in terms of what they provide to their customers. Um, and this is just, see at the bottom, this is just a small sample of the 2,600 plus companies that use Gurobi specifically. And again, this is just sort of our set. And if you want to think of mathematical optimization more broadly, there are a lot of other companies that use optimization, but maybe not just Gurobi at this point. But so it's used by everyone um, for the most part. So, what problems does it solve? Let's look specifically at the NFL's case. Again, in the previous slide, I talked about how scheduling is a common application of mathematical optimization. Well, the National Football League uses Gurobi as the engine to solve what could be one of the hardest scheduling problems that may just exist in business today, is creating the NFL schedule. If you think about how complicated this problem can be, there are, you have your 32 teams playing over now 18 weeks, 17 games. You're looking at different locations, not just home and away, but games that are being played overseas in Europe or in Mexico, and also looking into broadcast rights, considering that, and trying to make sure that you're getting the most eyes on the best matchups. That's an extremely difficult problem, and the NFL uses Gurobi to help solve that problem. But a couple other applications that we have on our website. So check out our resources at Gurobi.com, which don't worry, I'll be plugging that every so often, so make sure that you'll get there. But optimizing sort of scarce water resources and subscription box service optimization are just, again, a couple of the use cases that we have that you can take a look at. And again, just small examples, or small set of examples that mathematical optimization is used for. So now that we took a quick look at some of the industries that use mathematical optimization and the business problems that they solve, let's take a look at predictive analytics versus prescriptive. These are some terms that you may be familiar with, and you also may be familiar with a visualization that's similar to what you see here, where you have a measure of, and I'm going to air quote, complexity here on the horizontal axis, with the value it can bring to business on the vertical axis. And what we did here was we highlighted the typical data science workflow in blue. So things like descriptive analytics, moving on to diagnostic, moving up to what is typically the culminating part of a data science project, predictive analytics. So answering the question of what do we think will happen next. That's all part of the typical machine learning process flow, typical data science workflow. But what you see on the vertical axis is planning and executing. And that's something that predictive analytics just doesn't really do all that well. It doesn't give you the action, doesn't decide what you should be doing with the information that it's presenting you. It's not really super well suited for that type of question. And that's where prescriptive analytics comes in. You may know what the future may hold, but even if you have in some questions, some problems, even if you have perfect information, just the sheer sort of number of possibilities that you're encountering for some of these problems is so large that, again, with even perfect information, you're not going to be able to make the optimal decision. So that's where a rigorous tool like mathematical optimization comes into play. So that's what prescriptive analytics really tells you is what course of action should I be taking, what decisions should I be making in order to best sort of plan and execute for the future. And again, that's something that machine learning really doesn't do well. Again, it'll tell you what can happen next, but not what to do. And one thing that I want to highlight about this visualization and ones that are similar is that you don't necessarily need to be an expert in predictive analytics to move up to prescriptive. It's not necessarily a pure flow of I need to go from descriptive to diagnostic to predictive, all the way up to prescriptive, and that's the only time when I can get there. You can start the prescriptive analytics process at any time, more or less, and that essentially what happens, or essentially what you're looking, or what's going to happen, is when you mature, in the sort of the data science aspect of the things in blue, your mathematical optimization model is only going to get better. But you can build the foundations of an optimization model at any point. They're data science tools, machine learning, and is a very complementary tool to mathematical optimization. So moving in the next slide, I will talk a little bit more about understanding when mathematical optimization is the right tool. So let's hop over there now. So after comparing and contrasting predictive analytics with prescriptive, you may be thinking, okay, well, since they do sort of answer different questions, more or less, when is mathematical optimization the right tool? Well, to answer that question, let's start with another question. What is mathematical optimization? So let's define sort of the characteristics that you're looking for to identify a mathematical optimization problem. So mathematical optimization, it's an approach to solving complex sort of decision problems where you have a few things. One is you're trying to find the best course of action among many possibilities, and what many is, we'll define that a little bit later, but it is a lot. And there are things that the decision maker can set, so you actually have control over some of these things. It's not just random. You can set the price of something. You can build a facility. You can manufacture products. You can. These are things that you actually have control over. But you have limitations. You can't buy all of the ad space that you want. You have budgets, things like that. You have limitations to your actual decision problem. But you have a particular objective in mind. So you want to do something like minimize costs or maximize revenue. But it doesn't have to be something always like that. We talked a lot about scheduling earlier on. Maybe your objective is to create a very balanced schedule. So how do you take a decision problem that has these characteristics and then translate that into an optimization model? Well, you do that with algebraic notation, and this is what we call writing a formulation of an optimization model. So we see some color coding here. So let's look at the things on the left and how they relate to the formulation on the right. So the things that the decision maker can set, those we call decision variables. And these come with a couple different types. We have first what we call a continuous decision variable. So it's setting, an example of it is setting the price of produce. Comparing that to an integer decision variable where we're talking about like maybe manufacturing cars. If your optimal solution is to manufacture 127 and a half cars, that half is kind of a big deal. So, there are certain problems in which having integer solutions is very important. So that's something that you can specify for these problems. And then lastly, we have what we call a binary decision variable, which helps you understand alternatives. So yes, no, am I going to build a particular warehouse in a particular location? After that, we have our specific limitations, which we call constraints in an optimization model. So again, things like budget are common constraints. You can't for like a workforce planning model. You have to think about limitations on the number of days that people can work, number of hours that people can work, and things like that. But so the particular objective, that is what we call an objective function. And again, that's something that you're trying to maximize or minimize. So once you have all of this together in a nice, cool little formulation, this is where Gurobi comes in, because we haven't actually said anything about the optimal solution yet. We've just been uh, creating the formulation of our decision problem. So we've been translating it from words and text to math and algebra into symbols. Gurobi comes in to actually do the solving. So it takes your formulation that is coded up in something like Python or C, Java, R, whatever it may be, and actually provides the optimal solution. So again, what Gurobi is actually doing is it's the special sauce of finding the actual optimal solution. So we talked about a few different, types of decision variables and things like that. So mathematical optimization isn't just like one type of problem. It has a couple classifications. So let's sort of go through the common ones, and while we're looking at our sort of general formulation that we have from the previous slide. So there are a lot of options actually for types of mathematical optimization problems or formulations, I should say. The first is what we call a linear program, and that is a mathematical optimization model that has a linear objective. So you're not multiplying decision variables together, has linear constraints, and the decision variables are continuous. Next, we have an integer linear program, and I put linear in brackets because sometimes you don't say that. You don't always say it. People will sometimes say just integer program, but that has the same number 1 and 2 from above, so linear objective, linear constraints. But as you can guess from the name, is that the decision variables are integer or binary. So specifically, sort of what that may look like is your decision variables x, instead of being between two numbers, they may be your binary decision variables are 0 and 1. And here's our first little bit of math notation. That symbol that comes after the x, that stands for an element of, but in our case it's really just read as just the word in. And the curly brackets define a set, and the things that are in the curly brackets define the elements of such set. So lastly, or not lastly, but next we have a mixed integer linear program, or just mixed integer program, or MIP for short. And it has the same 1 as 2 as in an LP, so linear objective, linear constraints, but the decision variables can be part continuous. So you can have a set of decision variables that are continuous, and another set of decision variables that are integer or binary. And this is more or less the most common form of mathematical optimization model that you see sort of out in industry and out in the wild. And this is what we're going to be talking about. We're going to start with a linear program, but then we are going to work our way up to mixed integer actually pretty quickly. And there are other things like quadratic programs, QPs. QCP stands for quadratically constrained, so your constraints have some quadratic terms. And the MI is mixed integer, so you can sort of see how this all sort of comes together to talk about a bunch of different types of problems. There are also things about convex problems, non-convex problems, and things that have to do with uncertainty, like stochastic programming, and there's a whole bunch of things, that I can go down a huge rabbit hole, but we're going to stay with sort of what we have described so far, and I guess to relate to what we talked about before, or what I'm going to talk about in a little bit, is I'm actually going to describe a quadratic program in the next slide. So we talked about machine learning and the questions that it kind of answers, and then mathematical optimization, and answers different sets of questions. Let's talk about predictions versus actions and decisions. How can these things work together? Well, the most common way, and let's look at our general linear programming formulation, is to estimate the parameters of these of a mathematical optimization problem. And a parameter of a mathematical optimization problem is different than a parameter of a machine learning model, so keep that in mind. But those values, the C vector, A matrix, B vector, those are just numbers. Those are things that can be estimated using data that you have and machine learning models to come up with forecasts. So maybe B represents a demand, C represents a cost. Use machine learning to understand those values better. But that's not the only way that these two things can coexist. If you think about what machine learning is at its core, it is an optimization problem. You're minimizing a loss function. Whether you're maximizing accuracy, there's still a loss function that you're pushing down as much as you can, or you're minimizing error in like a regression problem. But not that's typically done in an unconstrained fashion, but it's not always like that. So constrained regression and feature selection, those are some ways that mathematical optimization can actually be used as an approach for a machine learning model. So if you're familiar with lasso regression, that is essentially a form of regression where you put a constraint on the parameters that you're estimating. And if you're not familiar with it, it uses the L1 norm, which is the absolute value, and essentially puts a constraint on the sum of the absolute values of the parameters that you're estimating in a regression model. Thinking about the L0 norm is the number of non-zero elements that you have in a vector or a set of numbers. So when you think about that, that's feature selection, because if your regression parameter that you're estimating is 0, then you're not selecting that feature. If it is non-zero, then you are. So using the L0 norm with regression in a constrained regression model, then that's essentially saying I want a certain number of features. And then lastly, I would start to talk about the L infinity norm. That is the maximum, that's the max magnitude of a set of numbers or a vector. So take the absolute value, whichever number is highest, that's your L infinity norm. And that ties into constrained regression, because if you wanted to do something like minimize the largest parameter value in a regression model, that would be minimizing the L infinity norm. So that's another form of constrained regression. And then another approach in machine learning that can be done with mathematical optimization is creating an optimal decision tree. And there's a lot of literature and papers that are on that. So that's something that I think could be interesting to look into if you're interested in that. So, all right, that's how these approaches work together. But how can you actually, how do you make this happen? How do you get machine learning and mathematical optimization to work together sort of in your workplace, on your team, in your company? And essentially, there's a couple ways to do that. Number one is see if there is a group of people that already do optimization modeling, that already know mathematical optimization. And if there is, and there very well could be, share information on projects to see if there's potential collaboration. We talked about so 5 things you're looking for a decision problem that may make you think that mathematical optimization is the right tool. Well, let's see if you have those things in your problem, and if you do, then maybe you can consult with this group within your company to sort of to work together to help solve that problem. And then, you can always just add mathematical optimization to your skill set. So make it as part of what you do. And hopefully that's what this training will help you on your journey. And if you're, once you get a better understanding and more comfortability and you understand how to sort of formulate and solve mathematical optimization models, you can build proof of concept models to help show the value of mathematical optimization within your organization. So now let's take a look at our decision problem, and this decision problem is going to be the basis of our hands-on notebook example that's coming up in a little bit. So pay attention. Let's say that you work for a company that makes and distributes widgets. I like the term widgets. It's fun to say, so that's what we're going to make and produce in this example. They're produced in factories and shipped to distribution centers. Your job as a data scientist is to create a machine learning model that forecasts widget demand by distribution center. So we see on the map that just popped up, the blue dots have a factory in them. Those are our production facilities. The orange dots have a truck in them, and they are distribution centers. So the company wants to reduce costs for transporting widgets from production facilities to distribution centers. Additionally, each production facility has a minimum that it needs to produce because it's up and running. We want to make sure that it's still being used, but it also has a maximum that it can produce. So it needs to lie somewhere in between there. And then each distribution location needs to be able to satisfy local demand. So we need to make sure that we're shipping enough widgets from the production facilities to each of the demand locations, or each of the distribution locations to meet demand. So from what I just talked about here, how does this fit into the criteria for a mathematical optimization problem? Hopefully a few things sort of rung a bell while I was describing this problem. So what we're going to do now is we're going to look at how to translate this decision problem into what we call a mathematical formulation. And then also we're going to start getting our first glimpses into Gurobi Pi, which is Gurobi's Python package that helps sort of really streamline this process. So what we have on the top left here is we have the actual sort of mathematical formulation for our problem. And it may look like, whoa, I see a bunch of sigmas and inequalities and things that, okay, what's going on here? Don't worry, we're going to go over each of these things sort of bit by bit. And so our goal here is to translate the decision problem to a mathematical formulation, and then also, while we're doing that, understand the corresponding Gurobi Pi code for each of the pieces that are highlighted above. So what we see on the top right is essentially, your first couple lines of any optimization problem done in Gurobi. Import Gurobi Pi as GP, and then from Gurobi Pi, import GRB. And what I want to highlight here is that this is actually something, these little cards that we're going to use to help illustrate this. We have a mathematical formulation card and a Gurobi Pi representation. We have actual PDFs that you can print out if you want to sort of play a little matching game on your own. So let's start translating. And so what we're going to do is we're going to sort of start popping up bits of the cards, and that they're going to represent parts of the formulation, and they're also going to represent the corresponding part of Gurobi Pi code, and then we're going to highlight what part of the math model that represents. So to start off any problem, you need to sort of understand that, hey, we need a model, and in Gurobi Pi you need to say, all right, let's define a model object. And that's going to sort of represent everything when everything's said and done. But at this point, it's just when you use the gp.model and you store that as an object, it is just an empty thing. We need to add all of these pieces, and that's what we're going to start doing. So in Gurobi Pi, the decision variables, the constraints, objectives, and all the things that we talked about are always associated with a particular model object. So we've just defined that we need a model. Okay, great. Well, what are the parts of that we need to start defining in order to build this model? Well, I didn't read off the individual cities for production sites and distribution locations, but we have them. So we have what we call a set of production sites, and those consist of the elements of cities of Cleveland, Baltimore, Little Rock, Birmingham, and Charleston. And then we also have our set of distribution locations, which the elements of that set are Columbia, Indianapolis, Lexington, Nashville, Richmond, and St. Louis. So we would put the elements of our set of production sites, and we can call that set P. And then we would call set D the set of distribution sites, which includes those cities. And we can sort of see on the right that the capital P represents the set, the lowercase p represents the individual elements of that set, and same thing for the capital and lowercase d. Remember that symbol in between just means essentially the word in, or you can also read it as an element of or elements of. But in typically is the way to go. And these are, again, what we call sets and subscripts of an optimization model. And they're important because it helps really define, it helps with readability of the model and understanding what are you representing in your model, in your system here that you're trying to algebraically represent. So it may seem like it's a little unnecessary to have this notation, and to some extent that's kind of true, but it really helps. It helps understanding this notation, understanding these bits and pieces here, really will help you be able to understand and sort of read other people's models, or read how people have formulated these types of problems, because it's essentially a universal way of representing mathematical optimization problems in an algebraic form. So so the sets and subscripts, these things are typically what we have as lists and sets in Python, and GrowBPy has a specific thing, what we call a tuple list. And we'll be providing links to what that really means, so you can dive in a little bit more. But you can use lists, you can use sets that you're familiar with in Python, but also at the same time that GrowBPy has its own sort of own similar way of looking at objects and sets. So the next bit of notation that we'd be looking at is, what is that upside down A all about? Well, that is essentially just a bit more notation, meaning that you read that symbol as just for all. And essentially what that symbol represents, as you can see in the GrowBPy card that's next to the big for all operator that's on the middle left part, it's essentially just a for loop, and it's saying for each element in this set, let's do something, or let's define something. So again, when you see that operator, just think of that as a for loop. So after that, we're talking about how we have a machine learning model that estimates demand. So we have a demand forecast for each distribution center. This is what we call data coefficients, or these values are also known as the parameters of a optimization model. So don't get that mixed up. The use of parameters there mixed up with parameters of a machine learning model. Those are different things. And again, the word parameter in machine learning and optimization, and the word model in machine learning mean different things. And that's something that Hassan's going to talk about in a little bit more detail down the road today. But the data coefficients, these are things, again, that we can estimate with machine learning models. Although, again, if you're not a machine learning expert, you don't have to use machine learning. This could be sort of numbers that come from subject matter experts, or maybe just simple averages, or descriptive statistics. That's perfectly fine. But again, to make your model as realistic as possible, then machine learning could be the best way to do that. But your data coefficients, those can be things that are stored in dictionaries, pandas series. Don't use pandas data frames. Make sure it's a series. But then also GrowBPy, again, has a couple of its own things, what we call a tuple dict and a multi-dict. Those are dictionaries that have some other properties that are specific to GuroBPy that help you define, that can help you really quickly define um, the data coefficients or parameters of an optimization model. Next, let's translate the actual decisions that we want to make. And what are we actually deciding here? And we talked about it, it was mentioned earlier, but what we want to decide is how many widgets each production facility should make and which distribution location it should supply. So we're going to denote that by the variable x, and I have that in a couple places. Sort of in the general model that we have, the math model, it's highlighted with the red back, and then so that x decision variable uses the subscripts p and d, which are the elements of our sets capital P and capital D. But so to get a little bit more concrete of what that's actually saying, that is for each element in the set. So we do have a particular decision variable x, sort of sub Cleveland, Indianapolis, and that is the amount of that's the number of widgets that are going to be produced in production facility Cleveland that will be then directly sent to Indianapolis. And so that's what our decision variables look like. And to add that to a GuroBPy model, we use model.addVar for adding a single variable, or addVars if you want to add a set of variables at once. So what I want to really emphasize here, because this is a mistake that I still make every so often, is that's for decision variables and constraints, there are those two different function calls for adding a single element, so adding a single variable or a single constraint, which we'll talk about in a minute, or adding a group of them, making sure that you have your addVar and addVars properly written up. That's an important tip. And then also, unless specified, both in the formulation and in GuroBPy, continuous and integer decision variables are assumed to be non-negative. It's a natural part of the problem. We've translated the decision variable in our decision problem. So let's turn our attention to the constraints of our problem. So in the text and how I described the problem verbally, we mentioned how each production facility has a minimum and maximum amount it can produce, and each distribution location needs to be able to satisfy a certain local demand, a certain amount of demand for widgets. So those are our constraints. And what they look like in the mathematical model is they look like sets of inequalities, and they can also be equality as well. And we'll see later on. I'll describe how the bottom inequality could actually probably be an equality if we wanted to, and for certain cases it wouldn't make much difference. But we have our sets of constraints, which we're going to represent as inequalities, and to add those to our mathematical optimization model in GuroBPy, we just call the model and then add the dot, add constr for a single constraint and constrs for multiple constraints. This is a little bit on the advanced side, but sort of thinking down the road, something to have in the back of your head. The add constraint command or a function can add any type of constraint. We talked about linear. I briefly mentioned quadratic. We also have what we call general constraints, which is again way down the road, but hopefully one day you'll be able to mess with those. They're really cool and make modeling pretty easy. If you have a large sparse matrix, then using add L constraint, constr, can be much faster in certain cases. So a little food for thought. And even as you progress through these problems and pass this course, hopefully, and you become a real exceptional mathematical optimization modeler. These are some things that hopefully you can have in the back of your head as hey, I can always improve things by really taking advantage of a lot of GrowBPy's functionality. So, so I was talking about how we have inequalities here. So an important part of translating the decision problem is to know specifically what type of constraint you have. So is it less than or equal to? Is it greater than or equal to? Or is it a strict inequality? I mentioned how in this case, an either or for the bottom constraint can work between an inequality and inequality. That's not always the case. Sometimes it is very, very, very important to make sure you understand which type of inequality that you have, or which type of constraint that you have, in order to make sure that your model behaves properly. So one tip and something that always tricks newcomers a little bit. We're used to be able to write inequalities in sort of a compact form where you have a center term and then two terms on the outside, and it's saying that, and actually I had this written, in the formulation before, that you have a variable that's between two numbers. When it comes to actually coding it up in GrowBPy, you can't. You essentially need to break something like what you see here, where you have 1 is less than or equal to x plus y, which is less than or equal to 2. You need to break that up into two constraints. So x plus y is greater than or equal to 1. Then also x plus y is less than or equal to 2 into two separate constraints. We have defined and translated our decision variables, defined and translated, our constraints. So let's look at the last major part of our optimization model, which is the objective function. And it wasn't explicitly said what the objective is, but we can infer what the objective really could be. So we said that the company wants to reduce the transportation costs of shipping widgets. Well, if you want to reduce the transportation costs, why not reduce them all the way by minimizing them? So that is our objective function. We want to minimize the transportation costs. And that is what that looks like in the math formulation is highlighted on the right, where we have a cost parameter times our decision variable, and we're adding all that up. And I'll talk more about the symbols there in a second. But in GrowBPy, it's just model set objective, and then we fill in the parts there. So a couple things is that linear programs don't accept multiplication between decision variables. I mentioned that earlier. Those are like quadratic or non-convex problems. But Groby does offer routines that work with that. You just need to understand what your problem is like. So if you do have that type of scenario, you do need to make sure that you're setting parameters right. If you don't, you'll get an error. So the last part that I'd like to quickly mention is summations. We saw them all over the place, and that's what that capital sigma is. And beneath that capital sigma is, in our case, a P or a D, and that represents the index that we're summing over. There's other operations that we may be doing, like multiplication or division of things, of particularly parameter values with relation to decision variables. The summation is typically done in GrowBPy with what we call gp.quicksum. It is more or less the preferred way of doing it, but it isn't the only way of summation in GrowBPy, and there are other ways to go about it. One that I listed here in the tips is just another way to go about it, and there are advantages for each method, and we'll discuss those as we go. So congratulations on making it through our first video together. Now we're going to be moving on to actually looking at our decision problem in much more detail. through modeling and coding hands-on exercises. And at this point, open up the Jupyter Notebook if you've already downloaded it, or click on the link for the Colab notebook to open that up. So yeah, let's get started.